That's source code for the Apollo guidance computer.
But look at that.
We were having a good time. They were worried it was going to fall on me. I liked the idea of stacking them up.
Millions watched Apollo 11 land, but almost nobody heard what happened next. While the world celebrated, NASA engineers were dealing with discoveries nobody had prepared for.
We had problems in many areas. It was a 7-day, 12-hour-a-day week at best, and at worst, we'd go 12, 14, 16 hours a day just to get the job done.
The moon was hiding strange things, and for a long time, nobody talked about it, until one Apollo 11 engineer finally broke the silence. After decades of speculations, what NASA found on the moon is finally coming to light. What were they not telling us? And how much did one mission change everything we thought we knew? Join us as we uncover the discoveries NASA made on the moon, revealed at last by the engineer who helped get them there. The mission that was never fully under control. On the 20th of July, 1969, the world watched in silence as two men descended toward the surface of the moon. The broadcast was calm, the commentary was measured, and the images beamed back to Earth carried the quiet authority of a mission going exactly to plan. That was the story the world believed. Inside Mission Control, the reality was something else entirely. As the lunar module Eagle dropped through the final stages of its descent, flight controllers began noticing readings that did not match their models. Altitude data drifted slightly outside the boundaries the simulations had predicted. The onboard guidance computer, operating at the edge of its capacity, triggered a series of alarm codes that nobody had seen during training. Engineers scrambled through reference documents, searching for answers in real time, with less than 2 minutes standing between the crew and the lunar surface. Then came the moment that nearly ended Apollo 11 before it began. Neil Armstrong looked through the descent window and saw what lay below him, not the smooth, open plain the mission planners had selected, but a boulder field stretching across the intended landing zone. Rocks the size of cars scattered across terrain that would have destroyed the lunar module on contact. Without hesitation, Armstrong took manual control, guiding the craft sideways across the surface while the fuel gauge continued to fall. Mission Control tracked the numbers in silence. The margin between success and catastrophe shrank with every passing second. Armstrong found his clearing and set the module down with less than 30 seconds of fuel remaining. NASA had reached the moon. But the moon had already delivered its first warning, and the hardest lessons were still waiting just beneath the surface. The simulations that failed on the real moon. Before Apollo 11 ever left the ground, thousands of hours of preparation had gone into making sure the crew would be ready for anything the moon could throw at them. Engineers ran scenario after scenario in simulators built to replicate every system on the spacecraft. Pilots trained for equipment failure, communication loss, navigational errors, and emergency aborts. The mission planners believed they had thought of everything, but the moon had other ideas. The moment Armstrong and Aldrin began their descent, the lunar environment started behaving in ways that no simulation had fully captured. The lighting conditions on the surface were unlike anything the crews had practiced with. On Earth, light scatters through the atmosphere, softening shadows and giving objects a familiar depth. On the moon, there is no atmosphere at all. Sunlight strikes the surface directly, creating shadows so sharp and black they appear almost solid, while the surrounding terrain blazes with a brightness that makes distance and elevation nearly impossible to judge at a glance. Thomas Kelly and the teams who built the lunar module had done extraordinary work under extraordinary pressure. Margaret Hamilton and her software engineers had written the code that kept the mission alive when the computer began throwing alarm warnings during the descent. Their preparation saved the mission. But even the best preparation could not account for every variable a real environment could produce. Multiple conditions collided during that final approach in ways the simulations had never combined. Lighting, terrain irregularities, computer load, fuel consumption, and the pressure of real-time decision-making all arrived together in the same 2 minutes. The crews had trained for each problem separately. The moon delivered them all at once, and the dust had not even entered the picture yet. What the astronauts would bring back inside the lunar module would become one of the most dangerous and underestimated threats of the entire Apollo program. The landing site that nearly ended Apollo 11. Nobody watching the television broadcast that evening would have known how close it came to going wrong. The commentary was steady, the voices from mission control were measured, and the footage being transmitted back to Earth carried the quiet confidence of a program that had prepared for every possibility. As Eagle descended through the final approach corridor, Armstrong looked through the window and saw the terrain the guidance system was steering him toward. The selected landing zone, a relatively flat plane, chosen from orbital photography, was covered in rocks, craters, and broken ground that would have collapsed the landing legs on contact. A landing there would not have been a rough touchdown. It would have been the end of the mission and the end of the crew. Armstrong had been trained for exactly this kind of decision, but training and reality are two different things. He took manual control and began moving the spacecraft sideways across the surface, searching for ground flat enough to set down safely. Every second of that search burned fuel the mission could not afford to lose. Inside Mission Control, the fuel readings were being called out in real time. Controllers watched the numbers fall toward the abort threshold, the point at which the descent stage would have been jettisoned, and the crew pulled back toward orbit without ever touching the ground. Armstrong found his clearing with roughly 25 to 30 seconds of usable fuel remaining. He set the module down, cut the engine, and spoke the 11 words that would define the century. Apollo 11 had landed, but the dangers waiting on the surface were only just beginning. And the dust the astronauts disturbed the moment they stepped outside would prove far more threatening than anyone had anticipated. The rocks that rewrote planetary history. When Armstrong and Aldrin returned to the lunar module and began preparing for the journey home, they carried with them something that would quietly reshape the entire field of planetary science. Sealed inside carefully labeled containers, packed into the limited storage space of a spacecraft not designed for luxury, were 47 pounds of rock and soil collected from the lunar surface. When the material was analyzed in laboratories, the results challenged assumptions that had stood for decades. Radiometric dating revealed that several of the rocks collected during Apollo 11 were over 3.6 billion years old, meaning they had formed when the solar system itself was still in its early stages. Later Apollo missions would return samples exceeding 4 billion years in age, pushing the timeline even further back toward the moment of creation. The significance of this was difficult to overstate. On Earth, geological processes are constant and relentless. Plate tectonics grind ancient rock into new formations. Erosion strips surfaces down over millions of years. Rain, wind, and biological activity erase the record of the deep past. The oldest surviving rock formations on Earth give scientists only a partial picture of what the early solar system looked like. The Moon preserves what Earth has long since destroyed. Without an atmosphere, without liquid water, without the geological forces that constantly remake the surface of our own planet, the Moon had been holding the same material in place for billions of years, untouched and unchanged. Apollo 11 had not just collected rocks. It had recovered a frozen archive from the birth of the solar system. But preserved inside that same archive was something far more dangerous, something so small it was almost invisible, and yet capable of threatening the health of every astronaut who came into contact with it. The dust that nearly became a disaster. Nobody had expected the dust to be a problem. The mission planners had accounted for surface conditions, lighting, radiation, temperature extremes, and the mechanical demands of working in a vacuum. The dust seemed like a minor inconvenience at most, something the astronauts would brush off their suits before re-entering the lunar module and think nothing more of. That assumption was wrong in almost every way it could be wrong. When Armstrong and Aldrin climbed back inside Eagle and repressurized the cabin, fine particles of lunar dust that had clung to their suits were released into the enclosed atmosphere. The smell reached them almost immediately. Buzz Aldrin later described it as similar to burnt gunpowder, sharp and acrid in a way that felt wrong inside a spacecraft. Both astronauts experienced irritation in their eyes and throats, a response their bodies had produced to something the human respiratory system had never been designed to encounter. The reason lunar dust is so dangerous comes down to its structure. On Earth, dust and sand particles are shaped by billions of years of wind, water, and friction. Edges are worn smooth, corners are rounded, and the material that ends up in the air is relatively harmless to inhale. Lunar dust has never been processed by any of those forces. Under a microscope, the particles look like broken glass, jagged and sharp at every edge, shaped by meteorite impacts and the raw energy of the space environment. The electrostatic charge the moon's surface carries causes the dust to cling to everything it touches, suits, equipment, visors, and instrument panels, making it nearly impossible to clean off effectively. As later Apollo missions returned to the surface, equipment failures linked to dust contamination became more frequent and more serious. The moon was not simply an empty place. It was an environment actively working against human machinery, and yet the dust, dangerous as it was, turned out to be one of the smaller threats. Above every astronaut who walked on the surface hung an invisible danger that the mission had survived almost entirely by chance. The radiation that could have killed them. The Earth is surrounded by a magnetic field that stretches far out into space, deflecting the constant stream of charged particles the Sun releases and shielding the surface below from the worst of what the cosmos sends in our direction. Above that shield sits the atmosphere, adding another layer of protection that filters radiation before it reaches human beings. The moon has neither. An astronaut standing on the lunar surface is fully exposed to cosmic radiation arriving from deep space and to solar particle events that the Sun releases with very little warning. During a major solar flare, the radiation output can increase dramatically within minutes, and the particles released travel fast enough to reach the moon in under an hour. The measurements recorded during Apollo 11 showed radiation levels that were manageable for the short duration of the mission. The astronauts received doses that stayed within the limits NASA had established as acceptable. Those numbers, however, came with an important condition attached. Apollo 11 flew during an unusually quiet period of solar activity. The Sun operates on an 11-year cycle of increasing and decreasing activity, and the timing of the mission placed it during a relatively calm phase. A major solar particle event during the moonwalk itself, something the Sun has produced without warning on many occasions throughout recorded history, would have delivered a radiation dose severe enough to cause acute radiation sickness in the hours that followed, and potentially fatal consequences within days. NASA was aware of this. Internal discussions about radiation shielding requirements for future long-duration lunar stays reflected how seriously the agency took the risk. The astronauts of Apollo 11 had not only reached the moon through extraordinary engineering and human skill, they had also benefited, in a way that could never be planned for, from good timing. The moon had allowed them to leave. But what it did to the ground beneath their feet when they did was something no one had prepared for at all. The moment the moon rang like a bell. After the astronauts of Apollo 11 returned to Earth, they left behind more than footprints and flagpoles. Positioned carefully on the lunar surface before departure was a seismometer, a sensitive instrument designed to detect movement within the moon itself and transmit the data back to scientists on Earth. The first meaningful test of that equipment came not from a natural event, but from a deliberate one. During later Apollo missions, NASA intentionally crashed spent rocket stages into the lunar surface at known locations and velocities, giving scientists a controlled experiment to measure how seismic energy moved through the moon's interior. The results shocked the entire scientific community. On Earth, when energy from an earthquake travels through the planet, it moves in a pattern that scientists understand well. The waves spread out, lose energy as they go, and die away within minutes. The behavior reflects the layered, partially liquid interior of the Earth, which absorbs and scatters seismic energy in predictable ways. The Moon behaved completely differently. When the rocket stages impacted the surface, the seismic signal did not die away quickly. Instead, it continued reverberating for an extraordinary length of time, in some cases lasting nearly an hour after impact. Scientists describe the behavior using a phrase that became one of the most repeated in the history of space exploration. The Moon, they said, rang like a bell. The scientific explanation for this involves the extreme dryness of the lunar interior. Without liquid or moisture to absorb seismic energy, vibrations continue bouncing through the rigid material for far longer than they would on Earth. The geology was unusual, but it was geology. What came next in the public conversation was something else entirely, and sorting the science from the speculation would take years of careful work. The answers, when they finally came, were buried far deeper than anyone had initially looked, hidden inside the Moon's own layered interior. The laser that proved the Moon is escaping Earth. Among the instruments Armstrong and Aldrin left behind on the lunar surface, one stands apart from the rest in terms of what it has continued to reveal in the decades since the mission ended. It is a small panel covered in specially designed mirrors, positioned on the ground with precise orientation during the brief hours the astronauts spent outside the lunar module. Scientists on Earth fire laser beams at this panel and measure how long the light takes to travel to the Moon and return. The precision of the measurement is extraordinary, accurate to within a few centimeters across a distance of roughly 380,000 kilometers. What those measurements have revealed, accumulated over more than 5 decades of regular observation, is something that changes the way it is possible to think about the relationship between the Earth and the Moon. The Moon is moving away from us. Every year, the Moon drifts approximately 3.8 centimeters further from Earth than it was the year before. The force driving this drift is the interaction between the Moon's gravitational pull and the tidal bulge it creates in Earth's oceans. Over vast stretches of geological time, this process has been slowing Earth's rotation and gradually increasing the distance between the two bodies. Evidence preserved in ancient rock formations on Earth supports this. Geological records suggest that hundreds of millions of years ago, Earth's day was significantly shorter than it is today, and the Moon appeared noticeably larger in the sky. And while the Moon drifts further away with each passing year, something on its surface remains completely frozen in time, preserved in a way that nothing on Earth can match. The footprints that may outlive humanity. On the 20th of July, 1969, Neil Armstrong pressed his boot into the fine gray dust of the Sea of Tranquility and made an impression that may outlast every city, monument, and structure humanity has ever built. The Moon has no atmosphere. Without air, there is no wind. Without wind, there is no erosion. The footprints Armstrong and Aldrin left during their 2.5 hours on the surface have not shifted or faded in any meaningful way since the moment they were made. Orbital imaging from missions launched decades after Apollo 11 confirmed this directly. The tracks, the abandoned equipment, the descent stage of the lunar module, all of it remains visible from above, completely undisturbed. The Moon is not entirely static. Micrometeorites strike the surface in a slow, constant bombardment that churns the uppermost layer of material across immense timescales. Scientists estimate it would take somewhere between 10 million and 100 million years for this process to erase the Apollo footprints entirely. Civilizations that do not yet exist may one day find them still waiting. The Moon may preserve evidence of humanity long after Earth itself has forgotten we were ever here. But what lies beneath that surface turned out to be far more layered and complex. complex than the scientists of the Apollo era had ever expected. The discovery hidden beneath the surface. The seismometers left behind by Apollo missions did more than record the strange reverberations that followed rocket impacts. Over years of continuous operation, they gathered data that allowed scientists to build a picture of something nobody had been able to see directly: the interior of the moon itself. The readings showed that the moon is not a uniform solid mass. It has a layered interior, with a crust, a mantle beneath that, and at its center, evidence of a partially molten metallic core. This structure closely mirrors the kind of internal layering found in rocky planets, including Earth. That discovery carried enormous weight. A moon with a differentiated interior, one that had separated into distinct layers during its early history, pointed strongly toward a violent and energetic origin. The evidence aligned closely with the giant impact hypothesis, the theory that the moon formed from the debris thrown into orbit when a Mars-sized body collided with the early Earth billions of years ago. Later, gravity mapping missions confirmed these findings and put hollow moon theories to rest permanently. Every answer the Apollo data provided seemed to open a deeper question, and the deepest one of all had been hiding inside the samples themselves for decades. If you enjoyed this video, like and subscribe, and also click the next video shown on your screen.